So hey everyone, I'm Arjun and I'll be doing today's tutorial. In particular, we look at two concrete problems that were raised by the community on various forums and how you can solve them using our newly minted support for Presburger arithmetic in MLIR. Don't worry if you don't know what all that Presburger stuff is, we will see to it shortly. Before I move on, I should mention that I'm the only one on stage here, but this is joint work with Kunal Grover, Tobias Grosser, and all the FPL contributors. In particular, Kunal actually prototyped much of the work in actually solving these problems with IR passes and also the user-facing interface of the library. Unfortunately, he couldn't be here due to visa issues. That's a photo of him. Maybe you see him around somewhere. So let's get into it. So recently, there seems to be a lot of interest in the polyhedral functionality that we have in MLIR. So the Affine dialect recently, some time ago, had a commit that used the mathematical functionality that we upstreamed, and also in CIRCT, in fact, there was a use of the affine dependence analysis that we refactored, simplified, and streamlined in the course of the FPL work. And thirdly, last year at the LLVM developer meeting, Florian Hahn presented a new approach to removing range checks. So essentially what he was doing was, take a look at this code snippet. So you have a standard vector, and you have an end, and you iterate from I equal to 0 till end, and just add up the elements. So in particular, note that we don't access data through the operator square brackets, but with @ and in case you've been working with no exceptions for a very long time, .at is supposed to throw an out of bounds exception if it's out of bounds. So this means that internally .at has a bounds check. Note also that in the beginning we have this assert that end is less equal to data.size, and you should be able to see that actually the bounds check should never be needed, assuming the assert holds. But we'll look into that in more detail soon. So let's inline this .at into the loop. So what we get is, if I is greater or equal to data.size, then you throw an exception. Otherwise, you just add the element at data sub I, and note that that operation does not do a bounds check. So if you take a look at the snippet we have here, this bounds check shouldn't be needed because firstly, we have an assert that end is less equal to data.size, and secondly, the loop bound is that I is less than end. And if you put these together, you can see that I is actually less than data.size always. And what we look at what we're going to implement is a pass that will actually infer this, collect these constraints, make this inference, and eliminate this user's bounds check. So that's the first concrete test case that we'll take a look at. The second one was actually inspired by a discourse post. So what they wanted to do was, they had these two subviews of a memref, and they were writing to both of them. So for example, say you were writing all ones to both of these subviews. And it turns out that in this case, when you write, the union of these two subviews is actually the whole original array. So you actually end up writing to the whole original array, and you can therefore simplify this IR into just writing to the base array. And they were asking if there is support for doing this kind of simplification in MLIR. So this again is something that you can do using the mathematical functionality that we've upstreamed. It essentially boils down to asking if the union of these two sets, which is the two subviews, is equal to the whole original set, which is the base array. And depending on what you're doing exactly, you may also need to check if the subviews here are disjoint, which also can be accomplished with what we upstreamed. So before we go into the implementation of these passes, let's just take a quick look at how we actually implemented this stuff. So in the old days, what used to be the case was that in LLVM, there was Poly, and Poly was a sub-project of LLVM that depended on ISL. ISL is essentially a third-party external dependency that could not be upstreamed into LLVM. And essentially, it was kind of all or nothing. Like if you want to use polyhedral stuff, you depend on poly or you depend on ISL, and essentially you take on a huge dependency. Which, for example, if you just want to check if two memrefs union to a base array, you probably don't want to use the entirety of ISL. And essentially, this polyhedral stuff was sort of quarantined in a corner of LLVM, and the main parts of LLVM did not always want to depend on that stuff. In MLIR, what we're hoping to have is that we have FPL actually part of MLIR. It's been developed within MLIR from the beginning. It follows the MLIR coding standards and documentation tests and etc. And we have members in the MLIR community who actually reviewed these patches and familiar with it. So, and also because it's part of MLIR and it's been developed for LLVM MLIR, we have first-class support for converting to and from the IR constructs. And as we will see later in the tutorial with the implementation of the passes, it's actually really easy to convert to and from the IR here. In the old case, there used to be a much larger impedance mismatch in doing this. Yes, so now let's come to the math for a while. So the basic thing that Presburger arithmetic deals with are integer polyhedra. Now what does this mean? It just means that you have a tuple of integers, say x and y, is subject to some linear, actually affine constraints. So for example, you have here 2x plus 2y greater or equal to 1, 2x plus 2y less equal to 13, 3y less equal to x plus 9, and 10y greater or equal to x. So this is a integer polyhedra that has two variables. It's defined by 4 linear inequalities. And an additional thing that we support is unions of these. So you can actually, instead of only having ands of these linear constraints, you can also have ors. This will come in handy later in the simplifying redundant checks. And this was something that we actually upstreamed into MLIR, which was not previously available. And these are just sets, and we have standard set operations on them: intersect, union, subtract, complement. We also have an operation where you can check if a set is empty, which comes in handy sometimes, as we see. And coalesce is a heuristic to simplify the representation of sets, and this also is useful. For example, if you have an if condition and you want to remove some redundant constraints in it, so it essentially just simplifies a condition. And a final thing that we need to understand before we go into the implementation of the pass is what the affine dialect is. So I'll go through this very briefly for the purposes of this tutorial. The affine dialect has two constructs for control flow. One is the for loop. This is not the exact syntax, but for understandability, let's use a simplified syntax. So the bounds of the loop are, for example, you have a for loop, I goes from 2s plus 4 to 3t plus 8. And here s and t are symbols that are outside of this loop. And you can also have a step 2, which means you go through the, you have a stride of 2 in the loop. So I plus equal to 2. And you also have an if condition. So here the condition has to be an and of some linear constraints. So like we saw in the polyhedron, you have I greater equal to 0, I less than n. These need to be like linear constraints. Now, what's interesting about the relation between affine and Presburger is that if you take a look at the set of I values that actually get executed in this loop, they form an integer polyhedron. So you have the variables I, S, T, and N, and you have the constraints, 2s plus 4 that's equal to I, that's equal to, and I that's equal to 3t plus 8. And so that should be 0 that's equal to I less than N. So this is the sort of connection between the integer polyhedron and the affine dialect. And in the sets that we have in FPL, we have 3 kinds of variables. So you can see that I and STN are sort of separated from each other. This is because I is a set dimension, which is like, for example, in this case, the loop iteration variable, whereas ST and N are symbols. So these are sort of like these correspond to symbols in the MLIR IR. For the purposes of this talk, you can consider them to be the same. Don't worry about it. What's interesting about these two things is that the variables in the set are directly related to the variables or symbols in the IR. And in fact, in the implementation of the library, you can attach an MLIR value to each of these variables. So you have a Presburger set that has variables I, S, T, and N, and you can say that I in the Presburger set actually corresponds to the MLIR value object, which is the actual value in the IR. Now there's a third kind which does not have a value associated with it, which is locals. So here the local is the I flow div 2. So essentially I earlier said that you only have linear constraints like 2s plus 4 is equal to I, but that is actually an additional thing that we support, which is flow division. So I flow div 2. This is internally implemented by adding an extra ID, which is like an artificial ID, which you don't need to worry about too much. But the relevant part is that it doesn't have a MLIR value attached to it. Yeah, so these three kinds of IDs are combined together and they form what's called a Presburger space structure. So when we make a new set, we do it constructed out of this Presburger space, which tells it how many kinds of each ID it has and what value each ID is attached to. So yeah, as you can see, the set dimensions and the symbols are attached to the IR via the values, and the locals are not. And the last thing I tell you about spaces is that it's about merging. So you might have two sets that actually are from different spaces. For example, I could have one set that only has the S and T here, and I could have another set that has N. And when you intersect these two, the resulting set will have all three of them, because the resulting set has constraints from both the individual sets. Yeah, so that's that about this. So now let's actually get to what you promised, which is a solution to a problem that was proposed in the previous dev meeting. So let's say, so this is basically an AST, that kind of thing that corresponds to the C++ example that I showed you earlier. So for convenience, I've written the assert as an if and an unreachable. So if n is less equal to size, we proceed into the loop. Otherwise, we go to the unreachable. So the loop, as before, goes from I equal to 0 to n. And then inside the loop, we have a condition that if I is equal to size, then we do the addition, total plus equal to whatever. And otherwise, we throw the exception. So how do we actually simplify this thing? So what we do is we associate an integer polyhedron with, as we walk through the AST, we have a context which is an integer polyhedron. Initially it's empty, and you see what I mean soon. So when I enter into the den of the if condition, I know that while I'm here, the constraint n less equal to size holds. So I add that constraint to the context, and now once again I enter into the body of the loop. Now I know that 0 less equal to I less than n holds. And so now whenever I encounter an if condition, I try to simplify the condition that it has given that the context holds. So in this case, I have a context saying n less equal to size and 0 less equal to I less than n. And now I will try to simplify the constraint I less than size. So actually, given this context, you can see that I being less than size is trivial. Like it always is the case. So you can actually simplify away this condition entirely and just have the total plus equal to. As compared to the implementation that we saw in the LLVM dev talk from last year, we have a much more robust mathematical framework where you can actually support many other things, like say you can support strides. So if instead of I++, you had I plus equal to 2, you can still support it because, as I mentioned earlier, you have support for those flow divs, which means that you can actually add modulo constraints. So for example, you can constrain that in this case, you have I equal to 2 times float div I by 2. And if you think about that, that basically says that I should be even. And another thing we can actually support is analyzing the else branch. So let's say that, I mean, in this example, it wouldn't make a lot of sense, but for example, if this if condition at the top had an additional constraint that size less equal to 1, so then if we had gone into the else branch, in the original implementation that we saw last year, it only supported ANDs of constraints. But here, because as I mentioned, we upstreamed into LLVM support for ORs, and we also support complements of sets. So in this case, we would say that the complement of this condition holds when you go into the else branch, which was not possible earlier. Okay, so that's enough for slides. Let's take a look at how this thing is actually implemented. Hope that's visible. Yeah. So this is the simplify affine if pass that we have. So get the operation. So initially we construct the context by passing the space. Did someone have a question? Okay. No, I don't think so. Yeah. So So we'll initially construct the set by providing the space, as I said. So initially there's nothing, but as we walk through the IR, we will end up adding more IDs and more constraints. So let's traverse the IR. If it's a region, we just recurse into every block and every operation and traverse it. And now let's come to the main part of the implementation. And if it's a for loop, we will add the for loops range constraints. So initially, we append a new ID. This corresponds to the induction variable of the for, so basically I. We add it as a ID of type setdim. So we have a new ID, and we actually provide these kind of helper functions to just add the for constraints. So in this case, we say add for affine for op domain. So this will add the domain constraints of that of I into surrounding constraints from the for op. And then you just traverse further. So the other case that we handle is if conditions. So we initialize an integer polyhedron called conditions, and we just add, once again, add affine if op domain. So this adds the constraints from the if op into conditions. And so I briefly talked about merging earlier. So basically we need to do that when the spaces of two sets could have different values, could correspond to different values in the IR. But just to not dwell on it too much, whenever you operate on two different sets, they might have different spaces, so you merge the IDs. And finally, we do the simplification of the condition, which is what we wanted to do in the first place. So we have the merged set, which is the context, and given that those context constraints hold, we want to simplify conditions. So we're doing that here. And now we just need to set the condition of the if op. So to do that, we need to know what actual IR, MLIR value each ID in the set corresponds to. So luckily we do know that, because as I mentioned, in the space, all the IDs are attached to MLIR values, and you can get them using conditions.getValues. So we just pass that to set if op.setConditional. So if op here is the IR if op. And finally, we need to convert from the integer polyhedron conditions, which is the mathematical structure that we have, into the IR level integer set. And to do that, we have a handy conversion function. It takes the context of the op and the set that you want to convert, and it just converts it. So That's it. That's all you need to do to set the new conditional from the mathematical object integer polyhedron. And we just traverse into the if and then regions. Yep. So to go into the if region, when we go into if region, we know that the condition holds. So we take the context and we intersect with the conditions. When we go into the else region, we know that the conditions don't hold. So in the previous work last year, this was not supported because the complement operation on sets is rather non-trivial because it produces unions of integer polyhedra. But yeah, we do support it. So all you have to do is say, conditions.complement, and we intersect that with the context and it recurs. So there was a recent discourse post about recursion, but for the purpose of this talk, I've just implemented this recursively. Yeah, so that was the affine if simplification. The other test case that I said I would show you was, so before we go into that, the two main things that we used there was how to add constraints from an if op, the conditions of an if op into a mathematical integer polyhedron. And the second thing was actually simplifying conditions given some constraints hold. So I'll quickly show you how these two things are done because they're like the most relevant part of what I just showed you. So actually, constructing an integer polyhedron from the if op is pretty easy. There's a constructor for it. I know it says flat affine value constraints here. That's the current implementation upstream, but eventually we hope to provide like a uniform interface where you would just use integer polyhedron maybe. But never mind those details. So you can just construct the mathematical object from the IR integer set. And then you remember that we need to associate values from the IR to the IDs of the set so that, for example, when we try to assign the conditional back from the mathematical object, it needed to know what each ID corresponded to. So we'll attach that here by saying, see a constraint set dot set values. And so finally, once again, we'll merge, which we always do when we operate between two sets. And finally, we intersect the new affine if constraints with the current set. So this is how easy it is to just take if conditions from the IR and add it into the mathematical integer polyhedron. The second interesting thing that we did was to simplify a condition, a set of conditions, given that some other context set holds. So how we do that is, first of all, we merge, which we always do, and then we use our implementation of the simplex algorithm. Don't worry about the details of that, but essentially it can tell you if an inequality is redundant given some context. So here we construct a simplex from the given constraint set, the context, and now we ask, given this context, we ask for each inequality in the set to be simplified. We ask for each of its inequalities whether it's redundant or not. Now, if it's redundant, we can just remove it, and otherwise we move on to the next inequality. So this might look a little funny, but so when you remove the ith inequality, the I plus 1th inequality comes to I, which is why we only increment I when you don't remove. But that's an implementation detail. The main takeaway from here is how easy it is to do this kind of redundancy checks using the Presburger library. Okay, so let's go to the next test case study that we had, which was a problem raised on the discourse post. So what they wanted to do was they had a memref and they had two subviews into it. And if you look at this in more detail, this is a memref of size 3x 512. So 3 and then 512 across. And we have two subviews into it. One starts at 0, 0 and has size 3, 256, stride 1. And the second one starts at 0, 256 and it also has sizes 3, 256. And if you take these together, you see that they actually span the whole 3 cross 512. So in this example, we're saying that we have a fill operation on both of these subviews. So we fill all the elements in both of these subviews with the same value. So in this case, since we know that the union of these two subviews forms the whole base array, we should be able to simplify this into a single fill operation that just operates on the entire base array. And in this case, we are writing a single value which is idempotent, so we don't need to care about each of the subviews being disjoint. But if we had a different operation, then we would have to do that. And I will also show you how we can do that with the library. Yeah. So let's go back to the. Yeah. So here we implemented the coalesce memref, which is the Subview Fusion that we talked about. So initially, this is a pretty simplified implementation. It doesn't support all the variants of the IR that it could. But the goal here is mostly to show you how to use the mathematical functionality. So I won't handle all the edge cases. So the first thing we do is we get all the fill-ups in the current block. If there are none, we can return. And the first thing, so we'll only support the case where every fill-up writes the same value. You could, aggregate fill-ups by value and handle each of them, but we won't do that here. So we get the value filled in the first operand and check that that's the same in every fill operation. And if it's not all the same, we can just return. And if they are the same, then we move on. And this is like IR stuff, so we just need to extract the subview from each fill operation that we have in this block. And if one of the fill operations is not acting on a subview, for the purpose of this tutorial, we'll just bail out. Again, like you could try to do something if you wanted to handle all the edge cases. If there are no subviews at all, then we can just return. And finally, all the subviews need to actually be part of the same base array, of course. There's no point in fusing subviews that have different base memrefs. So that's what we do here. And so now we've done with all the preliminary checks that check whether this pass actually makes any sense. Now finally, we come to the check that we showed in the diagram, where we need to check if the union of the two sets equals the whole base array. Sorry. So we know that all the memrefs have. So we need to first create a set that corresponds to the source memref. So in this case, we extract the source memref type, and then we can get the rank of the source memref, and from that construct the source set as an integer polyhedron. And now we construct for every dimension the two constraints. Like basically each dimension has upper and lower bound constraints on what range of values it takes. So it can be from 0 to the length -1. And that's the set corresponding to the whole base array. Now we'll construct the set that is the set of locations that are actually getting filled. So that's the fill set. So this exists in the same space as the other set. And now we go through each subview that we have, and for each of them, we similarly add the upper and lower bounds. Now, again, for the sake of this tutorial, we are only considering static strides and static sizes and stuff. So our constraints are going to be like for each dimension of the subview I, we have a lower bound, which is the offset of the subview in that dimension, and the upper bound will be, the offset plus the size minus 1, which is the last element of this is the last value that can exist in that dimension in the subview. So we're iterating through all the subviews. For every subview, we create an integer polyhedron. For every integer polyhedron, for a subview, we add the upper and lower bounds for every dimension. So for now, let's ignore the case of strides. We will come back to this later. For now, assume that the stride is 1, which means that the constraints we've added actually model the subview correctly. And so this is what I mentioned earlier, which is that we will see how to do the disjointness check, which is just by saying that the set of filled points that already exist, which is fill set that we've been accumulating into, should have no intersection with the new subview. So this is the union of all the subviews before. This is the new subview, and we say that their intersection should be empty. So this would be a check to see if all the subviews are disjoint. But for this particular thing, it does not really matter. But I just wanted to show you that that's also possible. And so if you reach till here, we have constructed an integer polyhedron corresponding to the set of points that lie in the subview, and we just union it into the fill set. So finally, fill set contains all the points across all subviews that get filled, and we just need to check if that's equal to the source set, which is all the points that exist in the base array. So we have the equality check in the Presburger library. We just need to call into it. So we say fill set dot is equal Presburger set source set. So fill set is a Presburger set because it's a union of integer polyhedrons, which I mentioned earlier. And if they're not equal, then it wouldn't be correct to replace it by the base array, so we return. And if they are equal, we simply replace all these fill operations with a single one. So this is basically to show you how the interaction between the IR and the mathematical part works. It's not to show you all the edge cases in the IR. So there are many more things we could support, which we haven't done. So let's look at the stride part, which is also something that is supported after our upstreaming efforts and was not available earlier. So what do we need to do to support the stride? What we need is that the value of the variable minus its initial value modulo the step should be 0. So basically, IV takes values, the lower bound, the lower one plus step, lower bound plus 2 into step, and so on. So that essentially means that IV minus lower bound should be a multiple of step. That means that IV minus lower bound should be step into Q, where Q is the floor division of IV minus lower bound by step. So this is the same thing we saw earlier, where if you wanted to say that I is even, we said that I is equal to 2 times I floor div 2. So here we want to say that IV minus lower bound is a multiple of step. So we say IV minus lower bound is equal to step times IV minus lower bound floor div step. So first we need to add this, like I mentioned earlier, we support these floor divs by adding local IDs, which are essentially fake IDs that just represent this floor division's value. So So we create the dividend. So dividend essentially has a coefficient of 1 for the iteration variable, and its constant term is minus offset. And yeah, we just need to add this local flow div, which is the local ID corresponding to this flow division. And then the second constraint we need to add is the actual equality that we talked about here. So yeah, we just construct this equalities coefficients, which has 1 for the iteration variable I and has a constant term of minus offset. And finally, has a coefficient of minus step for the artificial local flow division variable that we just added. And we add this equality constraint into the integer polyhedron for the subview. So yeah, so this is how you would support flow divisions. This can be abstracted into like a function for the integer polyhedron saying add mod constraint or something like that. But I thought that it would be useful to show a little bit more of how to work directly with the library in case you need to. So yeah, so that's the implementation of fusing these subviews if they are actually equal to their source array. Yeah. Great. So now before we conclude, let me briefly just talk about our upstreaming experience here. So one thing we were able to do is actually significantly simplify some parts of the affine analysis code base by removing these many duplicated and convoluted things which calls into the mathematical Presburger library. So that was very fun. And so before we started our upstreaming efforts, there was limited support for intersection, but they didn't have the merging stuff, and there was some support for emptiness checks, but it was an inexact heuristic. And after our upstreaming effort, we have the union, intersection, subtraction, equality, emptiness, and Lexman. So that's nice. We have a growing developer community. There's, I think, 5 people who have contributed to FPL already. You know, we started with less than that. So the contributions have been picking up recently, which is really good. And yeah, all this functionality is available today in the LLVM project monorepo. It's in the directory MLIR include. It's an MLIR analysis Presburger. So yeah, take a look if you think that some of the things I showed you today would be useful for you. Yeah. And to conclude, we looked at how to use the Presburger library to do some simple simplifications in the affine dialect, and we also took a look at doing things beyond just affine. It's actually useful throughout in many areas. And yeah, I talked briefly about the deep integration of FPL into MLR and the easy conversions from IR to math and how to use it in Affine. And finally, you can check out our project page, which is currently hosted at grosser.science/FPL if you would like to know more. Thank you.
Thank you, Arjun. Okay, we have a few minutes for questions. Are there any questions? Yes. Microphone coming behind you.
Thank you. This was very nice talk. It was very instructive for people like me who are less familiar with integer set. Oh, so yeah, sorry, my voice is low. It's just the way it is today. So I have 2 questions. One is FPL. There is a link between FPL and Affine, but can FPL be used by other MLIR dialect like LLVM? Is that possible? I guess what I wanted just to double check.
Yeah, definitely. So, for example, the second example I showed was with memrefs, which is like a very generic not specific to Affine, and also it's also used in CIRCT actually.
Right.
Yeah.
Okay, cool. And the second question is, what are the features that are missing? What is the future work of FPL? That's what I.
Yeah, that's a good question. So, for example, there's one issue right now, which is that all the analysis is done with 64-bit integers, but when you do some of these things like emptiness checks or linear programming, the numbers can blow up. So we need to find some way of bringing in arbitrary position in to actually support this without silently miscompiling if some overflow happens. We do have some prototypes for that, but we are happy to hear more ideas from the community of how we can do that. We had a previous work where we did what was called transposition, where you would start with 64-bit or a smaller type, and that would be really fast, and then only if an overflow occurred, you would switch to arbitrary position kind of things. So that's one thing we're looking at, but that's not upstream yet. It was only in a fork.
Okay.
Yeah, but yeah.
Right. Thank you.
Yeah, thanks.
Question.
Thanks for the tutorial and also for working on this in general. So I've been involved with a use case in CIRCT, and I can say that really helped us out there to have the dependence analysis available. So we are using it on the Affine dialect, so not on our own dialects, but still very useful. So my question is, I saw you referencing simplex there, so I guess linear programming is involved in the math that underlie that. Can you say a few words how the queries on these integer polyhedrons relate to linear programming, just out of curiosity?
Sorry, what was the question? Like linear programming?
Yeah, so how do you use linear programming to answer these queries, like is the set empty and so?
Yeah, so if you I can actually show you with the if condition. So essentially you have the context that we saw was a set of linear constraints, right? And so if you take a look at some of the conditions we have, so for example, we have a condition I less than size. So how we would check whether this condition can be simplified using linear programming is, so the objective would be size minus I, and the constraints would be the context n less equal to size and 0 less equal to I less than n. So you find out the minimum value that size minus I can take. And if the minimum is 0 or less, then it can never occur. Wait, I think it might be the other way around. But so if the maximum value that size minus I can take is 0, then this if always goes to else, right? And similarly, if the minimum value that size minus I can take is 1, then you always end up in the den branch, right? So this is an objective maximization problem. So, and the constraints are linear, the objective is linear, so you can do linear programming. Yeah.
More questions, yeah?
Thank you. So you obviously replaced a lot of the sort of handwritten, half-finished implementations, and you talked about how much code that removed. But what was the effect on compile time from changing from these, I assume, simpler implementations to now like a full math-based implementation?
Yeah. So in MLIR, we took a look at this, and it turns out that the rest of MLIR is much slower, such that this is not a bottleneck. Yeah.
Any more questions or comments? Yeah. Behind you.
So I'll ask this as an end user who can use this library. So do you have a mechanism where I can, so currently as I understand it, you extract the constraints from a given if condition or a loop, right? So is it possible like I can throw some constraints into this library and get the final output, instead of getting it from an existing loop or a if condition.
Sorry, can you repeat? You want to do what with the constraint?
I can feed the constraints to this particular library and I can get a simplified output.
Simplified in what sense?
Like in case of Subview Fusion, right? I can give a couple of constraints and it gives me a fused output. It's just about enhancing probably like.
So this can be implemented? Like as I showed that you can implement this kind of thing, like we don't have this upstream yet, but yeah, I mean, if there's a use case and we're happy to collaborate with people to implement like, their particular use cases that build on top of the library. So this is just the mathematical foundations and there's a lot more infrastructure, like your use case and the examples I showed, which we'll be building out in the coming time.
Okay, yeah, thank you.
Any more questions? Any more comments? Arjun, thank you very much for your talk.
Thank you.